I'd like to now look at an example of finding ground speed in bearings, and I'm going to use a trig approach. So in this particular example, make sure that you don't look at the examples that they have online, because those examples are going to be worked differently than I'm working this particular problem. Okay, this example says that an airplane has an airspeed of 540 kilometers per hour and is flying on a bearing of north 45 degrees east. The wind velocity is 30 kilometers per hour from a bearing of north 30 degrees west. Draw the resultant vector representing the path of the plane relative to the ground. What is the ground speed of the plane, and what is the plane's resulting direction? Okay, first of all, a little bit of clarification as far as terminology. Okay, airspeed, that's the actual reading on the plane speedometer. Ground speed is the sum of the airspeed and the wind vectors. In other words, the airplane speedometer might say that it's flying 540 kilometers per hour, but having a wind is going to affect the plane's ground speed. Okay. On this particular problem, it is essential that we draw a picture of what's happening. So we'll start that. And this picture is going to be detailed. It's going to be a little bit lengthy. Okay, so just be prepared. All right, first of all, we'll draw the bearing of the plane. So we're going to use our north line. And it said that the bearing of the plane was north 45 degrees east. And so we'll draw that out. That angle in here, 45 degrees. This was north. And then there is that vector. Now, I call it a vector because we know that the magnitude of that vector is 540. That's how fast the plane was flying. Now, on wind, we agree that from any particular location in this drawing, the wind is going to be blowing from the same direction. The wind was blowing at a bearing of north 30 degrees east, and so, north 30 degrees west. And so what I'm going to do is, first of all, look at that at the origin. In other words, if I'm looking at that particular point, then the wind bearing is going to look something like this. Okay, from the north line, it's blowing 30 degrees towards the west. And so basically, think about the wind is coming in at this direction, blowing on that origin, okay, in a direction of north and then 30 degrees west. And what I'll do there is I'll actually create that same situation and that same setup over here on the plane at the very, very end of this side. So I'm going to do this, a line basically parallel to the one that I just drew, and I'm saying that that's representing the direction of the wind. Now, on here, I'm going to be a little bit more specific. It said that the wind was blowing at a rate of 30 miles per hour, so I'm going to create a vector of length 30 from that tail end of that vector over. Now what this does is it creates a resulting vector from my starting position on up. I'm going to call that R. Okay, now the length or the magnitude of that vector is going to represent the ground speed. From here, I need to somehow set up some trig or set up some things so that I can solve this resulting triangle. Okay, now on here, what I'm going to do is I'm going to create some similar situations. Okay, we have, first of all, our wind. Y'all agree that the two blue lines that I have drawn are parallel to each other. I'm also going to draw another north line going straight up. The two north lines are parallel to each other. Okay, that being the case, from the north line down to where the wind is, we see from my picture over here, that's 30 degrees. Okay, let me move this 30. That 30 there is actually the length, and I don't want to get it confused with the angle. I'm going to put the length of 30 there on the inside. I'm going to underline that, and then the 30 degrees here on the outside. Okay, so that's 30 degrees. Also, I'm going to go ahead and kind of extend this line out a little bit. From the north line, the angle between the north line and that line, we can see originally was the 45-degree angle, so we can copy that up. Okay, and from there, we can find the angle that's inside of here. Okay, let's call that angle alpha. Okay, alpha we can find by taking 180 degrees, and we can subtract off 30 and subtract off 45, and that will give us there the angle inside. That angle is 105 degrees. Okay. Now basically what we're wanting to do is we're wanting to solve the triangle that I have right in here. Okay, and to solve that triangle, I'd like to first of all find R. Well, right now alpha, I have the angle that's opposite of R. I also have two other sides. I have one side is 540 and the other side is 30. And so that being the case, I can use my law of cosines to find R. So R squared equals 540 squared plus 30 squared minus minus 2 times 540 times 30 times the cosine of the angle opposite, which is 105 degrees. Okay, I'm going to skip a little bit of work. R ends up equaling 548.5305252, and this would be kilometers per hour. Okay, now R is representing the ground speed. Okay. The other thing it asked for in this problem, it asked for, once I found the ground speed, it wanted to know the direction of the plane, that resulted from its speed and the wind. To be able to do that, I need to find out the angle from the north line over to that resultant vector. I think to do that, what I'll first do is I'll come inside of here, and I will find this angle. Let's call that beta. Okay. If I can find beta, I can find theta by subtracting 45 minus beta. So I'm going to put a little note out here to the side. This is kind of my general plan. Okay, my general plan is I want to find theta. To find that, I can take 45 degrees and subtract off beta. All right, now how am I going to find beta? I can find beta by using law of sines. In other words, at this particular point, I know all my sides and all the angles except for, or one angle, and so I could use that angle to find beta. So down below, let's say that we have sine of beta over the side opposite of that, which is the 30, equals, and then I'm going to use what I found up above, sine of 105 degrees. The side opposite of it is the value that I just found. Okay, and I can solve this, and I'll end up with sine of beta equals 0.0528280077. And then if I take the inverse, I find out that beta equals 3.028231525. Okay, now my intent is I need to come up above and I need to find actually theta. To find theta, I take 45 minus the beta that I just found. So theta equals 45 degrees minus the angle from my work above. And so theta equals 41.97176.847. And the question was, what's the resulting direction? And so I would say that the resulting direction would end up being from the north line 41.97176.847 degrees, and then that was towards the east from our drawing up above. This concludes this example of ground speed and bearings.